All right, you guys, so we are going to practice solving logarithmic equations. So just a review of what we've been doing and things that you've already seen before. So hopefully we can go through this pretty quickly. So first question here, we're going to be solving for x. Notice that x is in the exponent. So why don't you guys start this one? As in terms of a first step, I would suggest combining these two numbers that are inside the parentheses here and then see what you can do next. All right, put me on pause and then we'll check after. All right, so to check our work here, like I mentioned, first thing I did is combine these two numbers. Then I converted this from being in an exponential form to being in log form. And I know that looks kind of funky here because we're used to seeing logs with a whole number base, but we can still do it with decimals. And then I plugged that into my calculator. I got that that's about 1.226, and then divided by 3 and got x. All right, next one. We're going to solve again, and in terms of a first step, hopefully you guys can recognize since I have two logs on this side, we want to start by condensing. So go ahead and put me on pause. All right, so as I mentioned, first I started by condensing these logs. So I got that if I have a sum of logs, I can make that a log of a product. So that's x times x plus 4. If I were to distribute that x inside here as such, I get x squared plus 4x. I went from log to exponential form, which gave me a quadratic that was factorable. And notice here that x equals -5 is extraneous because if I plug this in to log base 5 of x, well, log base 5 of -5 is not possible, right? Because we can't have a log of a negative number. So I have one solution. Why don't you guys try this one? Very similar to the one we just saw. Go ahead and put me on pause. Okay, so the first couple steps are pretty basic, right? So I'm going to condense the natural log, I'm going to distribute the x, and then I'm going to put this into exponential form, which is what you see here in purple. Now, if I were to get this all to one side and set equal to 0, obviously having that e there is going to make that difficult to factor. So what I chose to do was complete the square. You guys could probably use quadratic formula if you wanted. Totally up to you. But I did complete the square. So to get this term that I added to both sides, I did b divided by 2 squared, so 1 divided by 2 squared. So that ended up being 1/4. I factored the right-hand side, which is x plus 1/2 quantity squared. Square both sides, and then solve. Now keep in mind that for my final solution, I only list the positive one, -1/2, plus the square root of 1/4 plus e. And similar to the previous one, it's just because the negative one would make this extraneous. All right, let's have you guys try this one. Go ahead and put me on pause. Okay, so I started by condensing the logs, and what I noticed is that on each side I get a single log on both sides. Both of them have a base of 2, so I'm actually able to set their inputs equal to each other and then solve that quadratic. Once again, I do have an extraneous solution of -3. Think about if I were to plug that back in. So I have one solution, x equals 2. Okay, let's see if you guys can do this one. This is one that I would recommend factoring to begin with. So go ahead and put me on pause. All right, so for this one, this is factorable. If you're really not sure where this comes from, you could, of course, use u substitution, as you might have learned a while ago. You could say that u squared is e to the 2x, and then just u is e to the x. So if we really wanted to, we could write this as u squared minus 5u plus 6, and then factor this using u's. Or if you don't need to use that and you can kind of see how this factors just with the e to the x is in there, this factors nicely to be e to the x minus 3, e to the x minus 2, set those equal to 0, and I get two solutions, neither of which are extraneous. All right, let's try this one. I'd recommend solving using GCF. Go ahead and put me on pause. Okay, so as I mentioned before, I'd start this one by taking out a GCF, which I did. I took out the x times e to the -x, and I was left with -x plus 2. Now, since I all these factors, I set each of these equal to 0. I set x equal to 0. I set e to the negative x equal to 0. And I set negative x plus 2 equal to 0. So these ones are pretty simple. The x equals 0 and then the x equals 2. But this one here in the middle where I have e to the negative x equals 0, well, if I convert that to a log, notice that I get natural log of 0 equals negative x, but natural log of 0 is undefined. So, no bueno. Next one. This is definitely a challenging one, but we can do it. Why don't you guys go ahead and put me on pause and see if you can try it, okay? All right, so this one's a little bit funky because we have these two exponentials set equal to each other, and they have different bases. And also we got this random z in here, so that seems weird. If you guys notice in my first step, I took the natural log of both sides. And if you're wondering if I can actually do that, yes, of course I can do that. What I do to one side, I did to the other side, so booyah. Next, I use some rules of logs to simplify this a little bit. Notice that I took the exponents of the logs and multiplied them in the front. That's kind of nice. From there, all I did is I distributed this natural log of 2 into both terms. That's the only thing that's changed in this step. Here, notice that I got both terms that have the x on the same side. So here's the x, no x's on the right-hand side. And I took out a GCF of x. Took out a GCF of x here, and what was remaining I divided to the other side. Kind of ugly, but not so bad. Ooh, word problems, yippee! It says that the number y of endangered animal species in the world from 1996 through 2009 can be modeled by the equation below, where t represents the year with t equals 6 corresponding to 1996. During which year did the number of endangered animal species reach 923? Question mark. Okay, so if we want to know when, right, during the year, we're solving for t. So this 923 is representing the number of endangered animal species, so that's got to go in for y. So let's start by replacing y with 923. Okay, so now this is just an equation we can solve. So why don't you guys go ahead, put me on pause, and solve for t. All right, so for this one, I started to solve for t, right? I isolated the natural log of t, and once I got to that point, I converted to an exponential, so I got that t was about 16.403. Now we have to think about the context of this problem, and we're told that t equals 6 corresponds with 1996, right? So that's an important detail to help us actually figure out what actual year would the number of endangered animal species reach 923. So if I take this number, right, and I compare that, I figure out that during 2006, that's when the number of endangered species reached 923. Yippee!